Okay, we're going to find dy dx in terms of theta, where we have this polar equation, r is equal to secant squared theta. And to do this, we have two choices. The first one is to use that giant formula for dy dx in the polar world. But in order to do so, we have to remember that really well. And in fact, I don't like that formula too much. So let me show you guys this way. We have to know that any polar equation can be written in terms of a parametric equation. And that's exactly how that giant formula came from. Anyway, let me show you how to do that. So to write this in terms of a parametric equation, we will end up with x and y equations, right? And what we are going to do for the x is that we take r, which is the function of theta. Let's write that down first, which is secant squared theta. And for the x component, we multiply by cosine theta. And then for y, we put this down, which is once again the secant squared theta, but we multiply by the sine theta for the y component. And as you can see, whenever, if you're willing to just write a polar equation in terms of a parametric equation, just make this change. Maybe we can simplify things quite well. For example, this right here, secant squared theta is the same as saying 1 over cosine squared theta, and then when you multiply by another cosine theta, guess what? This and that cancel out, so you just have 1 over cosine theta. In another word, this is just 1 cosine theta, like this, right? One of them. And then for this one, if you can do the same thing, here we have power. I don't like that too much. So let me do that again. 1 over cosine squared theta times sine theta. Right? Here, this is the same as saying cosine theta times cosine theta. And if you pair things up, even though I cannot cancel them out, but when I do sine theta over cosine theta, I get tangent theta, isn't it? So let me look at this as 1 over cosine theta first, which is secant theta, and then sine theta over cosine theta, which is tangent theta. If you want to do this, you don't have to worry about the power, because you know when you do the derivative of something to a power, especially a trig function, sometimes it can be tricky, right? So in my opinion, this will be preferred. All right, so we are good to go. In order for us to find dy dx, we have to find dy d theta, dx d theta, right? Because we're using d theta, theta in here, not t, but same thing anyway. All right, so let me write this down. Dy dx is going to be, on the top we have dy d theta over, on the bottom we have dx d theta. Okay, dy d theta, look at this now, and then differentiate, all right? So this is the product of two functions. Both of them are just to the first power, which is much better compared to something to the second power times something else. Right here, we have to use the product rule, right? So let's do that, and I will put this down in red and blue. I will keep the first function, which is secant theta, and then I will multiply by the derivative of the second. Derivative of tangent theta is secant squared theta, right? And then we add it with, we keep the second function, which is tangent theta, and we multiply by the derivative of the first. Derivative of secant theta is secant theta tangent theta, like this. And for the dx d theta, we are differentiating x with respect to theta. We just have to do the derivative of secant theta, which is just secant theta tangent theta, like this, isn't it? So that's pretty nice. And is there anything you can simplify? Depending on how you want to do it, you can, put this together as secant to a third power and then put this together, but you still have to split the fraction anyway. Up to you. I will put them together just to make you guys happy. So this and that together is secant to a third power theta plus tangent, right? So we can write this, well, let's write down the secant theta first. And then tangent square theta, like this. And from here, I will split the fraction, all right? So first one, secant third power theta over this denominator, secant theta tangent theta, and then we add this with secant theta tangent square theta over same denominator, secant theta tangent theta. All right, what can we do? For the first one, this one and this one can cancel out. So we have secant square over tangent, right? Like this. And then for this one, as you can see, secant cancel, tangent, and we can cancel one of them, just like that. Pretty nice, right? Okay, I think we can simplify this a little bit more, so we'll do that, because this one, we have secant squared theta. Let's write everything in terms of sine cosine. That will be 1 over cosine squared theta, right? And then we have 1 over tangent theta. We do the reciprocal. Instead of sine over cosine, we will end up with cosine theta over sine, because this is technically a cotangent, right? Okay, for this, plus, I think I'm just going to keep it as how it is, tangent theta. Right here, as you can see, cosine cancel out, but we still have one more left. Anyway, we have 1 over cosine theta is what? That it's secant theta, and then multiplied by 1 over sine theta, which is what? Cosecant theta. And then we add it with tangent theta, right? And this is it. This to be on the test. If you would like, of course, you can write tangent as sine theta over cosine theta, and if you really want, you can get a common denominator and add it up. But anyway, this is the answer on one of the multiple choice answer. So that's it.